Good evening, guys. Here we are on the eve of the final. It's about 2 a.m. and I can't sleep. And so I'm going to take us through the chromatic dispersion component of optics for spectroscopy. This was the homework that was due last Wednesday, June 1 at 10 p.m. It's now the 7th, and so if you haven't done this, you're kind of out of luck as far as getting credit for this assignment is concerned, but there's still good information to be gleaned from working this problem, and I found it helpful to go through it a second time, and so I'm going to do that for you guys here and now. And so I'll start out by reading problem 1, which is concerned with this prism we're seeing right here. And it says that a given spectrometer uses a flint glass equilateral prism. White light is directed onto the prism, as shown below, at an angle of 46 degrees to the normal. The light is dispersed into the visible spectrum. At what angle to the normal does the red light leave the prism? The index of refraction for red light in flint glass is 1.662. So we're given a lot of information here, and this might look a little intimidating at first, but it's really quite a simple problem to solve. We really only need Snell's law to tackle this. So we're given the angle of incident white light, the angle to the normal, which is 46 degrees. And from that, we can calculate the angle at which it's going to refract within the prism. And if we pull over here, you'll see how I set that up. Really quite simple, just a simple application of Snell's law. And so the angle you should come up with, assuming your values, your given values look like mine, is 25.64 degrees. Now I want to pull back over here. So again, we have this angle now. It's kind of hard to see. We have this one, and we have a second angle. We have an angle of 120 degrees there. Now we know that triangles have 180 degrees, and we now have two angles of that triangle, and so we can now solve for this third angle, which is going to be the angle of incident light at this boundary right here. And to do that, we just subtract 120 degrees plus 25.64 degrees from 80. We obtain 34.36 degrees there. And again, that's going to give us the incident angle, or the angle at which light is going to contact the boundary between prism and air. And so what this is asking for, again, is the angle to normal that red light leaves the prism. So again, we only need to apply Snell's law. And I've done that here. And if you'll have a look, we arrive at 69.72 degrees. Pretty straightforward. If you go to number 2, it asks, or rather it says, the spectrometer in the previous problem is now used to analyze green light. Now, what is the angular difference between the position in the previous problem for red light and the angular position for green light? The index of refraction for green light in the prism is 1.674. Again, we apply Snell's law. We're given the index of refraction for green light in the prism at 1.674. We're going to use the same angle of incident white light, which is 46 degrees. I should clarify, the index of refraction of air is just 1. And so to set up this problem, we take the sine of 46 and set that equal to 1.674 times sine theta, from which we should obtain 0.4297. We can take the inverse of that and arrive at 25.45 degrees. From there, we go through the same procedure that we did previously. We take 120 and this time 25.45 degrees away from 180. We arrive at 34.55 degrees. Again, that's the angle right here. It's the angle to the normal within the prism. And it's the, I guess the angle at which light contacts the prism air boundary. I guess you could think of it like that. And so it's ultimately asking for the angle at which green light leaves the prism. So we have all we need. Again, we take the product of 1.674 and the sine of 34.55, that angle we found previously, and we set that equal to sine theta. And from that, we should arrive at 0.9494, the inverse of which is going to be 71.69 degrees. Now, it's just asking for the difference between this value and the one we arrived at previously for red light within the prism, which is 69.72. We take the difference there, and we arrive at 1.97, which, yeah, is your answer to number 2. So, I hope that's somewhat helpful. I realize this is a little bit scattered, but again, I hope it's helpful to you, and good luck, everybody.